So now we're going to be going into part 2 of this section, so that'll be part H2. And here we are going to be actually witnessing what's happening on the picoscope, and I'm going to just describe how this audio amplifier is working. I showed this diagram here, which basically showed the gain, basically how much the voltage changes as we change the frequency, but now we're going to see it live. So what we need to do is we need to open the picoscope. We just come up with this, we have a sort of a random demonstration of what's happening of the voltage. Now, very interesting. Let's try to do something. In order to do something, let's first activate the signal generator. And what you can actually should be, if you hooked everything up correctly, you should be actually able to hear a noise at 1 kilohertz. And that noise is coming from the transducer. Right now, let's just put the trigger on correctly. This is auto. And let's just change the square. So the square wave doesn't work so well. It's not really a good one. You can hear it now. It's not loud enough. But with the square wave, you do have higher and lower frequency input, so you can hear that 1 kilohertz tune coming from. But when you turn it on to, you can hear it. I don't know if you guys can hear it here. I'm going to put the microphone a little bit closer. This has a more rich frequency, the spectrum. When I turn it on, turn it actually to the sine wave, you don't really get much sound here. Okay. Not sure why that is. But okay, so what we need to do is finish setting up everything. We're not just going to use our ears as the transducers to tell what's happening. Now we're going to turn on the second channel. And what do you know? We don't have much of anything going on, because we're actually at 1 kilohertz. We're at a very small amplitude. Probably, that other. The square wave excited some other frequencies which we were hearing at that point. But what we need to do to increase the value of the current, which is that red trace. So now we can actually hear pretty well. Okay, so it is, now we're going to go to around 40 kilohertz. We have some more current activity. It's definitely not what we like. So here's that. So we have some current there. The voltage probably is set correctly. In order to get a more clean value from this, we're going to increase the bits, which sort of adds a filter. So there you have it. You have a bit of you increase the bits, you essentially lowered the effective sampling and made a nice averaging feature. We can also then now increase this voltage to 2. And then you can sort of see that these, the sine wave is chopped off. So I have that knob. Remember that knob I kept talking about? I can change that knob, and if I increase it too much, you're going to get really fun values. So, but if you increase it, there's only a certain range of voltage output. It's approximately 12 volts peak to peak that this audio amplifier can spit out, and this is actually going to end up being the main limiting feature for this audio amplifier, because effectively to drive this transducer, as I'm going to explain, we need a lot more voltage. Because of the frequency jumping phenomenon, that the mechanical system is not stable. it's not going to react with the same resonance frequency as you're driving it. It's going to be changing a little bit depending on how the water is going to be literally moving inside of that bucket, so that will alter the resonance frequency enough to alter how much amplification we're getting. Thus, we won't be really getting effective cleaning. So we're going to have to pump up the voltage and perhaps use other techniques. But I just want to show this phenomenon right here, that this limit. So when I did that gain test before, I actually set this potentiometer to a certain limit that I knew it wouldn't it wouldn't result in a cutoff. So right now, what I would like to do is a couple of things. I want to add measurements. Channel A RMS, and I'm going to add a measurement. Channel B RMS. So I have those two values here. It helps me again to differentiate how the current is changing. Now, this current measurement method is not very good for off resonance measurements where you're getting a very small current. So we're actually still sort of off resonance. So I want to go to 41 kilohertz. And then let's go to 42. Let's go to 43. And there we have it. So this is that frequency moving phenomenon that we have. If you actually looked at the water, you may see a little bit of movement, and that's not necessarily just from your moving the table around. There's actually some movement there. So, and also another cool experiment is that if you want to look at the water and at the same time change this frequency, you can actually see the water move or shift around a little bit. So that's kind of cool, just seeing how sound is playing in. Again, the amplitude of voltage is not very large, so it's not effective at off resonance frequencies. But let's make this a little more stable looking. We're going to just make that 500, and we're going to just make that, I think 20 is good. So we're just seeing how the frequency is changing based off of, and as you can see, we have actually a strong signal at 50 milliohms, 50 millivolts from the current. So it does quite work well. If you just want to see what happens when I turn on to square wave, we get that behavior. We might also just, so if you do change to 43, so now what we would like to do is just get an estimate. The maximum amplitude we're getting around is about 50 milliohms, right? So if I type in 43.34, so we're actually past the resonance. So let's try 42.5, 42.6, 42.7, 8, 9. Seem to be at 43 actually. 41. I seem pretty close to 43. And that's where about this frequency signal is going unstable. It's going unstable again for the reason that I think I can have to go a little more. That's good. That's about as high as we should go. Now it's going a little bit crazier. You can see we're getting around 60 maximum volts. So essentially, you're not seeing the whole screen here. There's a trigger, as you can see. We are getting quite unstable behavior. And the reason for this is the water is moving around, which is changing the mechanical dynamics, the chemical resonance frequency, which we sort of take for granted to be the same all the time. And that's why we're going in phase and out of phase. When the resonance frequency changes from the frequency we're driving, immediately your current will drop, and you will not have much vibration. But then when the water settles back to its position, the resonance frequency again maybe changes back toward your driving frequency, and then the amplitude gets larger. So this sort of rocking back and forth motion of resonance frequency and amplitude keeps occurring over and over again. But if you sort of put something in there, this plastic bottle, if I put this plastic bottle, so we change the resonance. So right now I just put a plastic bottle inside. I'm sure you guys know what a plastic bottle is, and this is that sort of changed the thing. So let's just try it 43. See, now it sort of picks up. It doesn't really have necessarily that much of a rhyme. Shaking around a little bit. Also, we have that 10 bits on. So if you make that 8 again, you sort of see some of that noise. That this feature really helps with 10 bits, and that's actually how I made that gain measurement. I used that 10 bits over a resistor. Resistor is obviously very stable with regards to its current characteristics and frequency. So that really, that proved to me that my system is working correctly, and I don't have a lot of these features this audio amplifier is showing here, and this resonance frequency. So, all right. What is the next step that we need to do? The next step is that we realize we can get a significant amount of current. So we have about 60, let's say about 50. Okay, we have almost 100 milliamps. We have about 80. We have about 80. So let's just do this. We have voltage over inductor, and that's about 60. Let's say e to the minus 3. So current equals that times 1.5, right? And voltage is all. I'm doing everything RMS. Let's just do maximum voltage like that, 8.3. So power, sort of nominal way of calculating it, equals that times the current squared. So we have about 6.72 power. So the power is still quite small. If you want an idea about the impedance, you multiply the voltage and current, right? Impedance is 92 ohms, which is very within the range of what we saw earlier. And the power is very small. It's 6 milliwatts, about 7 milliwatts maximum. So we're actually looking for the watt range. We want watts. We want 100 times this. So we want at least 20, maybe 10 to 20 times this voltage. So we are really going to need to step up the voltage into this transducer to make the power input about 50 watts. Basically, what's going to happen is that this frequency shifting phenomenon, you're going to be driving this system not near its resonance frequency, but not exactly at the resonance frequency. Therefore, you might find ultrasonic transducers such as these being driven at 200 volts because it doesn't track the frequency. Therefore, it really relies on a high voltage to work, but not extremely high voltage that you would need to use at very low frequency, like 1 kilohertz. Right now, I'm going to pause this video and I'm going to return. I'm going to run a real quick test. As you can remember, we use this program to determine the gain, the frequency spectrum, and I mentioned that a couple videos ago. And I'm really going to that. You can email me for that program which I made in Python. It's basically going to sweep the frequency. I know the frequency is around 43 kilohertz, so I'm probably going to run a test from 40. I'll probably do this. I'll probably run a test from 42 kilohertz to 44 kilohertz. That's 220. That's 2,000 hertz. I'm going to run in steps of 10. So alright, 42K, 44 to 44K, and steps of 10, and we have a 500 ml loaded. I don't know if I mentioned that. I have 500 milliliters of water, which is 1 water bottle. Made it easy for me to calculate, and we also have a audio amplifier hooked up to that. So I'm going to start this, and it's going to take a little bit to finish, and I will come back quickly with the results. So we finished the measurement, and if you can remember, this is the admittance 1 over the impedance. So we see a maximum value here, and a little bit of instability, which I mentioned earlier. there is a non-symmetry between the approaching frequency to the resonance and the frequency when we're moving away. This is due to some of the nonlinearity at this higher power level, as well as I think what we would call some resonance instability. So when we open the file, we get this, and this impedance is actually calculated by understanding that there's a 325 ohm resistor attached to this voltage, the second channel 2 voltage. But since we know how to calculate voltage, we're just going to delete that first of all. So now we're going to do current. So total voltage, which I'll just put as that. It'll be the first column, about 200, right? That's the total voltage. And the current, which would be this voltage multiplied by 1.5. So channel 2 multiplied by 1.5, that's the current. Okay. Therefore, we can get the impedance. Looks good, actually. So now we're going to plot everything like that, and right now I'm just going to move this up. So I plotted those, and what you see actually here is only the resonance portion. I didn't use enough frequency, but we have this. If you want to go back to this area, if you have the frequency, or sorry, the impedance, and you have the frequency, and this again is log. Normally we used to see something like that. However, right now we had just captured this portion right here, which is what we're actually looking at when we see this. We can put it in terms of a logarithmic scale, which will help us to understand that a little better. Let's alter the starting frequency by what, 50. It's good. So there we have it. There we have that, and I'm just gonna copy and paste that right into here. This picture. So that's the impedance. We likely have something like that later. So this is the impedance Z of transducer, and the voltage for that system. Okay, the voltage for that would be 8.27 volts. That's it. Pretty much did not move from that. At the resonance frequency, got to about 8. So let's say it's about 8 volts. 8 volts, and that's what we excited. 8 volts RMS, and this is what we use to excite this transducer. I don't think it was large enough. We didn't get much current. If you want to look at the current, maximum current level, how about let's just make another plot of power. Well, we don't have the actual power. Let's look at the highest. Let's just trap that in. Right now, I'm just going to do conditional formatting to make this to make the lowest portion sort of pop out at us. Most, where is the most? So here is the most current we've had. Okay. So the power is the impedance, or the resistance in that case, times the current squared. So we have that 0.7 milliwatts. So we have 0.7 watts going into this transducer. What we really want is maybe 20 watts or 10 watts, something like that. So you want 10 times the power. So in order to get 10 times the power, you'd probably have to use around 80 volts at least, doing a minimum calculation. So we got a resonance, impedance of about 86.4 ohms. We got resonance frequency of, I gotta click on that to tell, 42980. Wasn't probably gonna find that just by 42 hertz. The bandwidth I didn't calculate here, but we can see that's pretty at 8 volts. So and we got 0.7. Put this correctly. The amount of current we got was 0.9. We got 90 milliamps from this, and we're using 8 volts again. 90 milliamps RMS, and we got 0.7. I think 7.2, right? 7.2 watts. So I think that's pretty actually high. We got 0.72 watts. But again, we're gonna need to up this by 10. The strategies to up this whole thing by 10 is to use, for example, a larger or a more capable audio amplifier. You could use what's called a Class E amplifier, which sort of uses a resonance circuit. But what I want to try next, if you would allow me, and I don't think you have a choice because I control whatever goes through this media. Basically, we're going to do a MOSFET with DC power supply. Basically, you have your DC power. Put that to ground. You have a capacitor. This is called a charging capacitor. You have a MOSFET. And I'm just going to show it to be basically a diode, keeping things from running down. That's a not really a MOSFET. And then you're just going to have this piezoelectric transducer there. Basically, when you hook this up, immediately this transducer is going to charge because it's a capacitor. But then what we're going to do is when this completely charges, we're going to activate this MOSFET, and it's going to drain all the voltage over and down into this side. So basically, and we're going to actually have to have a resistor just to limit the amount of current going through the system. But basically, through this system, we'll be able to charge and discharge. That's basically the two things we need to do: charge and discharge. That's how you can drive that's how you drive a capacitor or a crystal. You have to charge and discharge it. You can't just simply charge it and reduce this voltage down to 0 or disconnect it. You cannot disconnect it because the charge just remains. So we have to have that bleeding MOSFET driver, and I'm actually going to show that in the next video, hopefully, because I showed and I demonstrated in this video. We demonstrated that how an audio amplifier can be used for driving piezo. Unfortunately, it wasn't high enough voltage, and audio amplifiers don't really drive with high voltage, not high voltage, but it did significantly improve that characteristics of the picoscope itself. So I may consider just using it in the future for whatever other projects I do. If I want a little more voltage, a little more current, I may just use this audio amplifier, which actually worked really well. And we also use that transformer. That's another thing we did. So current. So also we use a sense inductor. What else did we do? Again, yeah. So all this, we're just gonna go over this circuit next time to get more voltage. We could have used conquered this with a, we could have attached a transformer here, and a transformer would then step up the voltage. And that step up voltage would be able to provide larger watts to the source while keeping the impedance, which the amplifier sees, to a minimum. That's another option. I had some amplifiers laying around here. I mean, some transformers laying around in my lab, but they weren't proper for the job. So I'm going to hold off on this transformer idea till later, perhaps. But I want to try using this method right here, this bleeding MOSFET with a DC power supply, because I can get it all up to 32 volts. That would be 16 volts peak to peak, which would be double the amount of volume I have for my amplifier. And so that would be interesting to see how that would work. But we may not do that. We may try the transformer, whichever one works. See you next time. Thanks for watching. Again, please email me with any comments. My website is learnpiezo.org. Caps are not necessary. And my contact info can be found there. Thanks for watching.